Hello and welcome to my YouTube channel. This is Ramani Online Mathematics. I want to take this opportunity to thank Mr. Salas. Thank you very much for what you did. Mr. Salas, yes. All right, so let's start with the solution to Laplace equation. Now, when it comes to Laplace equation, unlike the wave and the heat equation, where we have the initial conditions, Laplace equation do not or does not have initial conditions. So here we deals with boundary conditions alone. You should take note of that. Good. So now we are going to look at solve the Laplace equation. So this is the equation uxs plus uyy. One thing you realize was that for the way when the heat equation it was having time, but here it's not having time. So that's what we are going to consider. So this is the question given to us subjected to the boundary conditions. I said the Laplace equation has no initial condition but has boundary conditions. So these are the boundary conditions that we are going to consider. So uxs plus uyy equals 0. X is greater than 0. 0 is y is between 0 and 2. Subject to the boundary conditions. So these are the boundary conditions that we are going to consider. You realize that here the boundary condition is on y. Okay, the boundary condition is on y. So you should take note of that. I know the reason why I'm saying that. So let's start something. If let me take solution here. We know what to do first. First, we set our general equation to be x and y. Is that okay? Now, it is stated clearly that u of x at 0 equals u of x, comma 2 equals 0. So, it means that the boundary conditions is on what? Y. So, this is what we are going to do. We set that conditions where we said that when y is 0, what happened? When y is 0, what happened? U is already 0. That's why I said this u is 0. So when y is 0, we are going to have 0. I'm just substituting here equals x at x, y at 0, because this one is supposed to be written as u equals x at x, y at y. But when y is 0, this is what happened. And you know that we said that x is greater than 0. It means that s at x cannot be equal to 0. So y at 0 is what? Equals to 0. You apply the same process to this side. What we're also going to give you y at 2 equals 0. Because when you apply the same process, you get the same thing. So you say that y at x is not 0, but sorry, y x at 2 is not what? 0. It's not equals to 0. So this is what you're going to get. So our boundary condition is going to be set on x, y at 0, which is equal to 0, then y at 2, which is also equals to 0. So these are the boundary conditions that we are going to use. So you are going to work on this. Now, this is the general solution that you have set for yourself. So if you have set the general solution to be u equals x, y, that's what you have set. Means that you need to differentiate with respect to x. That's you differentiate two times with respect to y. So with respect to x, this is going to be x prime prime y. Then respect to y, this is going to give us x y prime prime. So this is what you get. So we then come and substitute here, which is u, let me write it here again, plus u equals 0. uxx is x prime prime y plus x y prime prime equals 0. So here, let me send the other one to the other side. This gives us negative. So we divide both sides by xy so that we get x prime prime over x equals negative y prime prime over y, which is equals to lambda. This is perfect. And you know what to do. You pick this one, you equate it to this, you pick this, you equate it to that. So this gives us x prime prime over x equals lambda, or negative y prime prime over y equals lambda. So in this case, I can have x prime prime minus, because if I say equals to lambda x, and then you see I'll have x prime prime minus lambda x equals 0. If I multiply through by the negative and the y, I'm going to have y prime prime equals negative lambda y. So y prime prime plus lambda y equals 0. So these are the two equations that we have. We are going to work with these two equations. Perfect. These are the two equations I'm going to work with. So I'm going to clean this side because I'm going to write a lot of things here. So I'll clean here. What I need is this. I will write these two equations through here because I'm going to use them. Perfect. So now we have our u. Let me stand here. I have my u to be equal to xy. That's what we set. When we solved, we have x prime prime minus lambda x equals 0. Then we also have y prime prime plus lambda y equals 0. Then the boundary condition that we said was y at 0 should give us 0. Then also y at 2 should give us what? 0. So these are the two boundary conditions that we are going to use. So first, I just want to ask this question. If this and that, which one are you going to use? Which one of them are you going to use? You're going to use this one because the boundary condition is on y. So that's what you use. It's not like we guess and we use anyone that you want to know. So we are going to consider the three cases. So case 1. We said that when lambda equals what? 0. So when lambda equals 0, because we are basing on this, so when lambda is equals 0, this is what we get. We will get y prime prime equals 0 because if I put 0 here, 0 times y is 0. Now, if you integrate this one 2 times, you are going to have y equals a y plus what? B. The integration, if you are confused with it, you can visit the heat equation or the wave equation, how I do the differentiation. It's the same thing. Is that okay? Now, we are now going to substitute this into this side. So first we substitute y at 0 equals 0. What means that y is 0, small y here is 0, and the big y too is 0. I don't know whether you are getting it. The big y is 0, the small y is 0. So we are going to have 0 equals a multiplied by 0 plus b, right? So this one goes to 0, leaving b equals 0. So if b is equals to 0, the same thing, let's substitute this into that. So y equals y of 2, right, equals 0. So small y is 2, then capital Y is 0. So we have 0 equals a multiplied by 2. Remember b was 0, so we don't need to bring b again. So we have divide through by 2, you have my a to be equals to 0. When it's happening, say that this equation yield what? Trivial solution. When you say trivial solution, it means that we are just getting zeros. So once a is 0, b is 0, if I substitute it into this equation, I'll get everything to be 0. So when it happens like that, it means that you need to go to the next case. Okay, so let's move to the next case. I'm going to clean this for the next case because of the size of the board. Now case number 2 says that, now let's look at something here. You see, when we are dealing with the wave and the heat equation, case number 2, we usually consider when lambda is greater than 0. But here, we will consider when lambda is less than 0 first, for a reason. The reason is this, is because here y prime prime plus lambda y equals 0. Because here is plus. If you consider the other one, you get a solution. So you need to work. So let's consider that when lambda is less than 0. So we say that let p to be equals to lambda to be equals to negative p squared. Okay, here you consider that one first. You can do the other one. If you get the solution, you work. After that, you come to this one, no problem with it. Okay. So now let's move on. When lambda is less than 0, it means that lambda should be negative p squared. So we are going to have y prime prime plus, negative p squared y equals 0. So you can say that r squared minus p squared equals 0. So my r squared equals to p squared. Means that my r will be plus or minus p. So you know how to write solution for this. Solution for this is going to be a e to the power py plus b e to the power negative py. Now let's substitute. We know that when y at 0 equals 0, so that wherever I see capital Y, I put 0 there. This one will be 0. P times 0 will be 0. E to the power 0 is 1. So I have A. The same thing will happen here. B. So I can make one necessary. B will equals negative A. Something like this. So this is what I'm going to do. Let's take the other one where we said that my y at 2 equals 0. Means that my capital Y is 0 equals A e to the power P is now 2. So I'm going to have, Y is 2. So I'm going to have 2P plus B e to the power negative 2P. So 0 equals A e to the power 2P minus A e to the power negative 2P. Alright? So for this case, if I factorize this one, I have A bracket of e to the power 2P minus e to the power negative 2P. But in this case, A will be 0 because there's no way that exponential functions can give you 0. So what we say that A is equals to 0. But e to the power 2p minus e to the power negative 2p is not equals to 0. When it happens like that, A is 0, so my B will also be 0 because B will be equals to that. So it tells you that this one too is yielding what? A trivial solution. So since this one is yielding a trivial solution, you move to the next case, which is when lambda is greater than what? 0. So now let's look at when lambda is greater than 0. So when lambda is greater than 0, we say that let p to equals to lambda to be equals to negative p squared. Sorry, positive p squared, right? That is when lambda is greater than 0. So this case, we have y prime prime plus y equals lambda y equals 0. So y prime prime plus p squared y equals 0. So r squared plus p squared equals 0. So my r squared will be equals negative p squared. So r will be negative, pi plus or minus, right? So I'm going to write a solution for this. So y will be equals to a cos py plus b sine py. So that's the solution for that. So we are going to substitute. We have when y at 0 equals 0. So capital Y is 0 equals cos 0 is 1. Because if I put 0 here, it will be p times 0, which is 0. Cos 0 is 1. 1 times a is a. Then sine 0 will be 0. 0 times b is b. So a is equals to 0. We also consider when y at 2 equals 0. So when I put that one here, I have 0 equals already a is 0. So 0 times this, everything goes to 0. B sine y is 2. So 2p. Right? Now what happened here is that we know that um, the b and the sine 2p. If we put any number here at all, what happened here is that this one can go to 0. So once we make this b become 0, then the thing comes to trivial solution again. So what you do here is that you say that b is not equals to 0. Once you make the b goes to 0, it becomes trivial solution. So that you consider on the sign. And how can we make this sign to go to 0? It's only when there's n pi what? There's a pi here, because when there's a pi here, sign times any number. So what you do here is that we say that let's 2p to be equal to n pi, where n equals 1, 2, 3, going. Is that okay? So that when I replace this 2p by the n pi, the pi, anytime I substitute any number, any of these numbers here, it will give us 0. So now you can say that this side is 0, then the b can stand so that we can work with it. So if you do this, let's try to make p the subject. I'm going to have p equals n pi over 2. Good. So you just come back to this place, then you substitute. So I'm going to substitute this one here into this. I'm coming back to the original equation. So I have y equals, but remember a is 0. 0 times everything there goes to 0, leaving. You see, normally we put n there because we have brought in n. So we have b subscript n, so that we have sine. Now, p is now n pi. So, and y is here. So we are going to have n pi y over 2. Please, when you finish, we don't come back here to substitute. No, we'll come back to the original equation. So when I substitute here, that's what I'm going to get. So I have something like this nicely. So I have solution for y. We need to get solution for what? X. So this is my x prime prime minus lambda x equals 0. Remember, for when it comes to this, we only consider one of the case. But one of the cases, the case that you're going to consider is the one that gave us a solution for y. And which of the cases that? That was case number 3, when lambda is greater than 0. So here we say that when we let lambda to be equals to p squared, is that okay? That's when lambda is greater than 0. So if that thing happen, you're going to have x prime prime minus p squared x equals 0. So you have r squared minus p squared equals 0. R squared equals p squared. So then you have r equals p plus or minus p. So let's write general solution for this. X is equals to a, okay, let me use different variables, c e to the power px plus d e to the power negative px. So this is what we have. C and then what? T. Perfect. So this is what we have. We are going to do something here. Because this one has no boundary condition, just like the y, you go straight to the point. So what you are going to do here is we are going to substitute this one into the equation that we found ourselves. Is that okay? That's what we are going to do. So let's do that substitution here. You know that my u is equals to x and y. So my u will be equals to c, then d. So I'm going to have c e to the power px plus d e to the power negative px. And this one is multiplied by bn sine n pi y over 2. There's something that is left behind. This one. The pp here, I have to change it, okay? Because we said that p is equal to n pi over 2. So here I'm supposed to replace it, this p, instead of p, I have to write it as n pi over 2. So I'm going to have n pi, remember there's x there, over 2. Here 2 is going to give us negative n pi x over 2. So these are the two things that I'm going to get. So you just remove the p and put that one there. And this is simple as that. So now at this point that we have, let me write a 10 top here. you have my u to be equal to, let me bring this one first. Bn sine n pi y over 2. Then I will open the brackets. Then this one comes in Cn e to the power n pi x over 2 plus C dn e to the power negative n pi x over 2. You close brackets so that I can clean this side. Okay, now this place, what you are going to do here is this. We have used this condition over the boundary condition here. Let me this one and that. So this one say that as u approaches 0, x approaches infinity. So if you look at these two that I have here, this one will not touch it because this is y. The focus will be on this 2. This one, if x approaches infinity, will I get u to be 0? The answer is no, because if x approaches infinity, means that when I put a bigger number at where the x is, I'm going to get a bigger number because this is an exponential function. So this one will be raising the power. So it will be bigger number. But what of this? For this one, yes, because of the negative here, it will be like 1 over e to the power n pi x over 2. So if this x approaches a bigger number, or infinity, that's a bigger number, you realize that this number become huge. And since this number become huge, it will approach 0. The u will approach 0. I don't know whether you understand what I'm saying. Yes. So what you can say here is that yes, this one is true. So the statement here is just asking us at which point will this one approach 0, the u. The point that this u approach 0 when x approaches infinity is this one. But this one cannot be. So you have to find a way to make this one approach what? 0. And for you to be able to find a way, that one can only happen when c subscript n is 0. When c subscript n is 0, the whole of this one will go to 0. So that the u goes to 0. So that's what we are trying to say. So when that happens, it means that the whole of this one will go to 0. So this one is out because 0 times this is out. Don't be confused with that, because how this one looks like, the question is just asking us at which point will this, the x, as x goes to infinity, which one of them will go to 0? Yes, this one will go to 0, but you want all of them to go to 0. In fact, not which one of them, but you want all of them. So we are able to notice, because of the negative, this one will go to what? 0. It will be approaching 0, but this one will be bigger number, so we want this one to go to 0 by saying that Cn equals 0. Okay, so if Cn equals 0, the only thing that will left behind will be b subscript n sine n pi y over 2. So this one goes already, dn e to the power negative n pi x over 2. This and that is multiplying. If they are multiplying, you can say that my u2. Let's replace dn. When you can have something like this. Let's replace it by small bn. So that I have small bn e to the power negative n pi x over 2 sine n pi y over 2. And you know what you are going to do? Because you say that this n is from 1 to infinity, you can write this one as a summation, so that I have this one, n start from 1 to where? Infinity. Bn e to the power negative n pi x all divided by 2 sine n pi y over 2. So this is what we have. Now, we are done with this. So we are now going to apply the third condition. The third condition is saying that u is 1, x is 0, y is y. So if u is 1, so we are going to have 1 equals x is 0. So if x is 0, This side, e to the power 0 will be 1. So I'm going to have 1 equals the integral n to infinity bn sine n pi y over 2. So this is what you are going to get at the end if you substitute the second one. But we need to get the bn. And this looks like sine. So we are going to apply the sine, Fourier sine, to solve this. Is that okay? Good. Let me explain this. You realize that this is the general solution. This is when after I apply the boundary condition that we had this. So after we get the bn here, you will just come and substitute it here. Then this becomes a particular solution. Is that okay? So let me clean that. So I have it here already. So let me rewrite this. When you do the substitution, you have 1 is equals to n to infinity bn sine n pi y over 2. This is what we have. So we are going to use Fourier sine. So my bn is equals to 2 over L. But here, remember our L, this is the boundary given 0 to 2. So our L will be 2. So let me go straight. I'm going to have 2 integral of f at x. But here f at x is 1. 1 sine. So 1 times. So that still gives you sine n pi y over 2 dy. Okay, so let's integrate this. This is easy to integrate. 2 over 2 is 1. So I have my bn equals now the boundary condition is 0 to 2. Okay. If you integrate cos, you get negative cos. If you integrate sine, you get negative cos. This one, if you integrate this, you are going to have all divided by ny over 2. So that will be 2 over n pi. You are going to get n pi over 2, all divided. So you get this. Bracket will be n pi y over 2. Then this one is from 0 to 2. How I integrated this? If you integrate, you get something like cos, negative cos n pi y over 2 divided by whatever that is here. You differentiate it. That gives you n pi. Or if you differentiate y, that gives you 1 over 2. And that's why if you simplify this, you get this. So you should take notes. So now here, I'm just going to substitute, okay? If I put 2 here, you see that I'm going to have n pi 2. And this 2 will cancel this, leaving n pi. And you already know that cos n pi is given as negative 1 to the power n. You know this. Good. So you shouldn't be confused with that. So bn equals negative 2 over n pi multiply by, so here give a negative 1 to the power n. Then minus, if I put 0 here, cos 0 is 1. But remember, already there's minus, so meeting this, that will become plus 2 over n pi. So here, I can write this one as bn equals 2 n pi out 1 minus 1 to the power n. Something like this. This one I'm going to have. So that is my bn. So I'm just going to substitute this one into the general solution. So let me clean here. So my general solution u is equals to summation n equals 1 Now my Bn is 2 over n pi bracket open 1 minus 1 to the power n. That's it for Bn. Then e to the power negative n pi x over 2 sine n pi y over 2. So this becomes the particular solution. But here, let's look at something. If you get to this place and you leave it, maybe it's okay. But let's check something. If n is 1, if I put 1 here, what am I going to get? That means here will still be 1. So I'm going to have negative, but that gives you positive 2, right? When n is 2, that will be positive. So when n is 2, that will be positive 2, a positive 1. So that gives you 0. When n is 3, you get still negative like that. So it tells you that anytime it is even number, you are getting 0. Anytime it is odd number, you are getting um like a number, not 0. So let's see. Okay, so this is what I'm trying to say. When n is 1, this one will give us a certain number. It won't be 0. When n is 2, everything here will be 0. If I put negative to the power 2, that will give us positive 1. 1 minus 1 is 0. When n is 3, this won't give us 0. When n is 4, it will be 0. N is 5, it won't give us 0. When n is 6, it will be 0. So it tells you that Bn, that's for Bn, okay, is this. Look. N, so 0 if n is what? Odd. Four over n pi if n is, okay, where if n is even and n is what? Odd. Because here, if I put 3 here, this is going to give us negative, that's positive 1, positive 2. So positive 2 times 2, that will give us 4. When it is 5, you still get it, that gives us 4. So this is what you get. So that's what you're going to do. It tells you that anytime it is even number, we get odd. Sorry, 0. But when it is odd, we get this. So instead of n, let's define the n in this manner. 2k minus 1. If you remember your introductory analysis, these things are proved. This is formula for odd functions or odd numbers. If I put 1 here, they say that where k is equals to 1, 2, 3 to infinity. If I put 1 here, 2 times 1 is 1 minus 1. That gives you odd. 2 there, 2 times 2 is 4. 4 minus 1, that gives us 3. That is odd. You can test them, you see that. So it tells you that our final answer here is going to be n to infinity 4 over, so we are using this, okay. And our n is 2k minus 1, so I'm going to have pi 2k minus 1 e to the power negative n pi x over 2 sine n pi y over 2. And this becomes our final answer. Thank you very much. Please let me come back here. Here, let's replace this n here by 2k minus 1, okay? So when you do that, I forgot to bring that. because you said the n is now 2k minus 1. So wherever you see n, you put 2k minus 1 there. Thank you. Bye bye.